So let's finish off chapter 10.4, and this will be the last section for our exam. So this is the very end of chapter 10. It's probably some of the harder stuff as well. So for some of the problems, I'll ask you just to set them up. And then for some of the other problems, I'll ask you to actually solve. Some of the setup itself is very difficult, and the problem will just become way too long. So let's continue on with chapter 10, finding area and lengths of polar coordinates. So this example we're going to talk about is when you have two polar graphs and you're trying to either find the area shared by them or the area on the outside. So previously in Calculus 1, I taught you guys how to do top curve minus bottom curve or right curve minus left curve. Okay, so what we're going to do in this section is sometimes you will have to subtract curves and other times you'll have to add curves. It really depends on each problem, so you got to be pretty careful. But in all problems, you need to draw a sketch. So let's draw a sketch of this. Oops. I'll make it a little bigger over here. So the first graph is going to be this guy. So I'm going to use red for this one, okay? So I'll use red for this curve, for this polar curve. And when I do that, I get something like this. And again, bear with me, guys, okay? I'm not the best. So we get a little cardioid like that, okay, on our graphing calculator. And we get another graph that's 2 plus cosine theta. So then this one looks something like this. I'll draw this guy in green. If I look on my calculator, it's something like this. And then does one of these, okay? So we have our two polar graphs, okay? And sometimes we'll have to, in this case, we kind of got lucky that they seem to intersect. And now we have to find the area. So what we need is the area shaded or shared by these two curves. So that would be this area here. That's what's shared by the two curves, correct? That's the area we're concerned with, okay? And including here. But the problem is it's because polar graphs are working like on a rotation, they're rotating around and part of the graph is drawn depending on when you stop on theta. So we did one full cycle. So what we're gonna do is we're gonna kind of shade this in and we're gonna find this area and this area, right? So something I want you guys to think about when you're doing this is note. So we're gonna try to walk the path of our curves and we're gonna take that area. So as you walk your path in a counter clockwise direction, your angle is, your angle should be increasing. Use symmetry when possible. Okay, so there's a lot of ways we could do this problem then, okay? But if I start, let's say that I start here, so I start right here, and I walk along this path here, okay? So I could say that this is negative pi halves, right? And this is positive pi halves. And then I could do, so I'm going to kind of show you guys something how we could do this. So then that means that that integral is the red one. So I'm going to do the integral from negative pi halves to pi halves, okay? And once again, we're going to do 1/2 the curve. So how do we find just that area in blue? We're going to do 2 minus 2 cosine theta, quantity squared, d theta. So that'll be that area. But then I need this secondary area right here. I need this secondary area right here. Oops, let me undo that. Let's try, instead of blue, let's go with yellow, okay? Or orange. So we need this area in here now. Now, where does that area start for the green? Well, once again, we have to walk. We're going to start here, and we're going to walk this way. So what is that calculation? And notice we're switching curves now. We went from the red curve to now we have to switch to the green curve. I'm sorry, we went from the red curve and now we're switching to the green curve. Okay, so I have to do that calculation, and that would be 1/2 the integral. So what are those angles now? Well, those angles will now be right here is now pi halves, and then right here is now 3 pi halves. So it's all about walking in a counterclockwise direction, and your angle has to continue to grow, okay? So now the thing is, that would find each piece of that area, but in order to make it the correct area, we have to add these two values together. And we're gonna be using 2 plus cosine theta squared d theta, right? So that would be the integral that would find the area of this. Now, as you can see, this would be a little bit of a beast, because you're going to have to do 2 minus 2 cosine theta, square that, FOIL that out, 2 plus cosine theta, square that. And in the past, if we would try to combine our two integrals to make some nice clean integral. However, because these are using different angles for our limits of integration, we can't. Now, we could kind of do something like this. Couldn't we just do, if we wanted to, couldn't we just say 1/2 the integral from 0 to pi halves of 2 minus 2 cosine theta squared d theta? So what I'm saying now is just do this one, find that, and then multiply by 2. That would work as well, right? So I could put my little times 2 right here, because I'd find this area and then I would double it, right? And I could do the same thing for the other part. I could go from pi halves to pi and then double that area. So this is an option for you guys using symmetry. So a lot of times symmetry is a very, very powerful tool in parametric, and I mean in polar curves, and also sometimes in parametric, but in polar curves, it has a heavy dose of symmetry. So you're going to oftentimes be able to make your integration much easier by using coordinates like 0 and or angles like 0 and you know, other easy angles, maybe pi, things that are easy to do sines, cosines, and tangents of, so you can calculate very quickly, right? So let's take a look at another one. This is one of my favorite ones. I'll try to find you guys some kind of test question like that, like this one. So example 2. Okay, so it says find the area in the first quadrant that is inside r equals 2 sine 2 theta and outside r equals 1. So we have a circle and we have a rose petal, it looks like. So let's take this and draw a little quick sketch. Okay, so I'm going to draw a quick little sketch. I'm going to use, I don't know, let's use blue for this guy. Let's use, or I guess we could use that kind of weird coloring for this guy. Okay, so that's going to be 2 sine theta. And again, I'm going to do my best, guys. And then this one is going to be r equals 1. So that's going to be a unit circle. Let's use this weird color for this guy, r equals 1. Okay, so for the circle, oh my gosh, that's my greatest circle ever. Okay, now let's not screw up the rose petal. Now let's do the rose petal. And it's going to go something like this. I'm a legend. Okay, and then we got now these are going to be bad. Yeah, I already screwed it up, but you guys get the idea, right? Honestly, this is the best I've ever done. In 10 years of teaching calculus, this is like the best I've ever drawn. This one's the only one that needs help. But here's the thing. Find the area in the first quadrant that is inside r equals 2 sine 2 theta. So let's find the area inside first. 2 sine 2 theta in the first quadrant. So that would be all of this, right? So this is what's inside my rose petal, okay? Then they say outside of r equals 1. Well, then the outside, then I'm only looking for this area right here. Okay, so this is really the only area that I'm trying to find. Okay, not all the yellow, just this part. Okay, so that means that I'm going to take the furthest away curve minus the closest curve. So the rose petal is furthest away. So that's going to be my integral. And that will be 2 sine 2 theta squared d theta. Now we have to put a 1/2 in front. And then we're going to subtract off the circle. And that would be 1/2. Well, in this case, r is 1 squared d theta. So this problem, instead of adding areas, we actually have to subtract them. So basically what we're doing is we're finding the area of the circle and subtracting it from the area of the rose petal. But the problem is we have to worry about the circle and the rose petal intersecting, right? And we have to worry about these angular boundaries, okay? So what we're gonna do is we're gonna find out where the rose and the circle intersect, and that is gonna help us find, or that is gonna help us determine these intersection points right here and right here. And that way we know how much of the circle we have to count, and then how much of it we subtract. I should say how much of the circle we're actually counting. We're only going to count the circle from here to here, right? We're not actually going to do all this area and all this area. So we have to be real careful with that, okay? So again, it's not terrible, but really drawing the sketch can really, you know, kind of make things a little more concrete for you, okay? So now let's clean this up. Oh, we got to find these values. Sorry about that. So let's say that 2 sine 2 theta is equal to 1, okay? We're gonna, you know, divide both sides by 2, so then we'll have sine 2 theta is equal to 1/2, right? So we're gonna take the arc sine of, well, you know what, we don't even have to get fancy like that. Basically, you guys know that when is sine of theta, so when is sine of theta equal to 1/2? Well, you guys should know that that means when theta is equal to, or let's say sine of x, when is sine of x equal to 1/2? Well, that means that x would have to equal what? What could you plug in for the sine and get 1/2 as your y coordinate? Well, you guys should know that that should be at pi 6 in quadrant 1. And when else? That should be in, let me see here. Well, let's draw their unit circle. So we have here, and when else would it be 1/2? Right here, I believe. So this is pi 6, and this is what, 5 pi over 6, I believe. Okay. So the problem is we don't have x equals. We have actually 2 theta equals. So we need to figure out when does 2 theta equal pi 6 and when does 2 theta equal 5 pi 6, right? Because those are the two angles that would give me 1/2. Well, then I solve this and I get theta is equal to pi over 12, and I get this theta is equal to 5 pi over 12. So these are now my two angles where the circle and the rose petal intersect in quadrant 1. So I can come up here and I can say pi 12 and 5 pi 12. I can say pi 12 and 5 pi 12, right? Now, luckily, these actually are the same limits of integration, so we can do a little bit of cleanup. So I'm going to factor out the 1/2, And this is going to be the integral from pi over 12 to 5 pi over 12. And again, hopefully you guys understood how I did this. If not, you could try to convert it. You know, there's all kinds of ways you could solve this, but I was just trying to do it without needing a calculator or anything, and just trying to think about it. So this would be 4 sine squared 2 theta minus 1, right? D theta. But we know that this is actually pi over 12, 5 pi over 12, okay? You know what, I could take this 4 out, and I could put the 4 outside, and this would cancel and cancel, and this would become a 1, and this would become a 2. And then inside would be sine squared 2 theta minus 1 d theta. That's a little bit cleaner, but still not good enough. You guys should also know that this guy right here is one of the problems we've been working with for the longest, since back in chapter 7, I believe, depending on the book, since way back when we had to reduce the power from a squared to a first power. So we're going to do 1 minus cosine of 4 theta. Remember, you have to double whatever the angle was, and then minus 1 d theta. And again, this is all cleanup. That's all I'm doing here. So now I should be able to get, let's see, if I pull the 2 out from both, this will be the integral of pi over 12, 5 pi over 12. I could cancel this 2 and then bring this 2 outside, but then that would make this have to have a division by 2. Yeah, so we could do that, and then this would become 1 minus cosine of 4 theta minus 1/2. Okay. But let me see here if this is going to work. Yeah, let's clean this up a little. Sorry about that, you guys. I'm just trying to see the cleanest way to write this. But then this would be the integral from pi over 12 to 5 pi over 12. And then this minus this would be 1/2 minus cosine 4 theta, d theta. Oops, I think I forgot my d theta right here. Yeah, I think that's it. Now the question becomes, let me clean this up right here. Now that would be the integral. Now, if we wanted to actually go through and solve this, let's see what we get. Hopefully I didn't make any silly mistakes. You guys will let me know when I talk to you if I made a silly mistake, but I think this is okay. Yeah, it's 1. Did I forget to distribute a 1 or anything like that? Or a negative? I don't think so, so this should be okay. So this is going to be, if I integrate this, this will be 1/2 theta minus, now this will actually be 1/4 sine of 4 theta. And then we're going from pi over 12 to 5 pi over 12. Remember, I just did a little baby u sub on this. U equals 4 theta, du equals 4 d theta. So you guys should be able to do a little u sub on that from there. I just kind of skipped that step where we've been doing this a while now. So now let's integrate, or let's do f of b minus f of a. Let's do the fundamental theorem of calculus. So this will be what? 5 pi over 24 minus 1/4 times the sine. Oh, geez. That's going to be what? 5 pi over 48, I guess. No, that's 20. I'm sorry. I'm doing this wrong. Let's do 20 pi over 12. We'll clean that up in a second. Now we have to minus f of b minus f of a. So this will be 1 over, or pi over 24 minus 1/4 sine. 4 times this would be 4 pi over 12. Well, that's going to end up being pi thirds. Okay, so let's see, 5 pi over 24. This is going to become, divide both sides by 4. This is going to become 5 pi over 3. So we should know that 5 pi thirds, let's take our unit circle. 5 pi thirds is probably right here, right? Because 6 pi thirds would be 2 pi. And that means that it matches this guy, and you guys know that this guy is 1/2 comma square root 3 over 2. So then this guy would become 1/2 comma negative square root 3 over 2. So we should get 1/4 minus 1/4 times the sign would be negative square root 3 over 2 minus pi over 24 plus 1/4 times 4 pi. So this will become 1/3 or pi over 3 pi thirds. And we know the sign of pi thirds is the square root of 3 over 2. So this is square root 3 over 2. I hope this cleans up. So this will now be 4 pi over 24. I'm using this guy and this guy as like terms. And then these two will be what? Plus square root 3 over 8 plus square root 3 over 8, which is 4 pi. This cancels with this, and this would become 6. So this would be pi over 6 plus 2 square roots of 3 over 8. But still not done. This is a rough one. Cancel, cancel. Plus square root 3 over 4. And that is actually the correct answer. We did it. Okay, so this is a tough one. And again, I can't give you like 20 of these. If you were taking the exam in class, I'd probably give you one. If we're taking the exam online, you might see one also like this, but you won't see a bunch of these. But I really do like this one because, believe it or not, this is the doable one. This is the one that's doable. Some of the other ones are much, much worse than this. And honestly, we were done with calculus from here, right? So everything from here down, this is just fractions. This is just being able to do trig and being able to do fractions. That's no longer a calculus problem. Okay, so you guys should be okay with this. Okay, so let me see here. I think that's good on that. I think you guys have a good set for there. Let me see here. Maybe I'll do a different one. I wanted to give you one arc length problem before I quit. So let's do an arc length. So we're going to do an arc length problem, and instead of going through the proof, I'm sure you've seen where arc length comes from. Thinking of like wrapping ribbons of infinite thinness around a shape, or that was for surface area, I'm sorry. Taking a bunch of little, so you have some curve and you take a bunch of little triangles, right? And you try to approximate the arc length using a bunch of little triangles. Now that's one triangle there, or we could have done in your Calc 1 class, your teacher should have given you a graph, something like this, where you do that. And then they take and they say, we want to calculate the length from here to, let's say, here. So in your class, you probably drew some kind of triangle like this, right? And you tried to use the Pythagorean theorem to build this little triangle right here. So you did a squared plus b squared using the differentials and everything like that. But then you said, but what if, one triangle is going to have a little bit of error. What if I wanted to use an infinite amount of triangles? So you drew a bunch of really small triangles here to try to approximate this length even more accurate. I can't really draw it that small, but you guys get the idea. You basically take a bunch of triangles and use them. And so it's very similar to the idea, or it is similar to the idea of the Riemann sum, but now we're doing it at infinity of triangles to calculate arc length. So hopefully you guys saw that in your previous class. So we're going to jump right into the formula that looks very similar to the arc length formula from Calc 1. So this will be our formula. L equals, or that's a really ugly L. So let's go L equals theta 1 to theta 2 of the square root of r squared plus dr d theta, quantity squared d theta, okay? So we'll do kind of a basic one, and then we'll probably call it a day on this video. This will pretty much be all you're going to be tested on from 10.4, this and then the previous video of 10.4. Again, 10.4 is kind of the meat of 10.3 or 10.4, you really have to be good at this. 10.3 was really more about like polar coordinates, how do they work, kind of a background, a slight review, but not a lot of calculus. 10.4 is now, okay, polar coordinates, how can we do calculus? And that's what I'm going to really focus on the exam. I might give you a few polar questions, but for just, you know, review, but that's more just to give you some opportunities to get some points. Okay, so in general, 10.4 is the thing that you should focus on for the exam. All right, from 10.3 or 10.4. So let's look. So it says find, this is example 3, I think. Find the length of r equals e to the 2 theta, okay, for 0 less than or equal to theta less than or equal to pi, okay? And remember, it's really important with polar and parametric is the when, because if you were going to draw a parametric curve and you went from 0 to pi, you wouldn't have the full shape. And that goes the same for polar curves. If I only tell you to go from like 0 to pi halves, you're not going to get a full rose petal. Even if you have the original graph, it's not going to give you the full thing. So you have to, you know, oftentimes find out how much it takes. You know, when you get a little more advanced, you might say, well, does it take 4 pi's to make the complete picture? Is 2 pi's enough? 1 revolution, depending. So the ones we've been working with, the majority of them, it'll take 2 pi, it will be 1 revolution and the entire picture will be drawn. But sometimes it might take 6 pi's until the entire picture is drawn. It really depends from problem to problem. So they gave us the when, right? So they gave us theta is between 0 and pi, okay? So we're going to have to find dr d theta. So the first thing we need is dr d theta, and that's going to be, so we have, oops, let's do this. Let's show that r equals e to the 2 theta. So we're going to ddr both sides, or I'm sorry, dd theta both sides, dd theta, dd theta. Okay, so this will be dr d theta, which we need, right? This is what we need right there. And then it's going to say is equal to e to the 2 theta times 2, right? So we have our dr d theta. So now we can just use the formula. So L equals the integral from 0 to pi. They told us these values. We didn't have to go hunting for them like we used to. And then we have the square root of r squared. So this would be e to the 2 theta quantity squared plus dr d theta, which would be 2e to the 2 theta quantity squared d theta, or not quantity squared, but the entire thing squared. And then area or length is equal to 0 to pi of the square root of e to the 4 theta plus 4e to the 4 theta d theta. Okay, well, that looks promising. Well, that's actually, those are like terms. We can actually clean that up. So this will become the square root of 5e to the 4 theta d theta. So then this becomes, let's see what, e to the 2 theta times the square root of 5 d theta, integral from 0 to pi. But we know that square root of 5 is just a constant. So then we have L equals square root of 5 integral from 0 to pi of e to the 2 theta d theta. Well, that's just the square root of 5. And then we're just going to do a little u sub. So this will be e to the 2 theta over 2 from 0 to pi. Oops. Well, that's not so bad. So then L is equal to the square root of 5 times e to the 2 pi over 2. You know what? I guess I could take the 2 out if I want as well. Let's put this over 2. E to the 2 pi minus e to the 0. So this will become the square root of 5 over 2 times e to the 2 pi minus 1. And that would be my final answer. That would be, oops, that would be my arc length. Okay, so my arc length of this graph, of this polar graph of e to the 2 theta, whatever that would look like, we could graph it, would be square root of 5 over 2 e to the 2 pi minus 1. And we have our arc length. So this is how you can calculate arc length. Let me see, I have one more. I don't have this one worked out, so hopefully I don't mess it up, but I don't know the answer to this. Let's kind of work on this together. So it says, oh, let's just set up the integral needed to find, that's why I don't have it worked out, because we don't actually find the answer. This one's pretty tough. We just want to know how we would find the answer. To find the length of r equals 1 plus sine theta let's see here, and then we need to find, oh, they want to know the entire thing. So note, you need to find the limits of integration. Okay, so let's look at this graph. So we have y equals 1 plus sine theta So this is what it looks like on my calculator. Hopefully we're both getting the same thing, or we're all getting the same thing. So let me try to trace this out. So I get something like this, and then something like this, and then something like this, okay? So it looks like another cardioid, okay? So now that we have this, they want to know the integral needed to find the length of r equals 1 plus sine theta. So I think we can do from 0 to 2 pi. Let's see here. Let's go to window. Let's go to second function pi, and let's see how much of the graph it does. Okay, so let's go to window. So I'm going to change my window, and I'm going to say, let's go by 3 second function pi divided by 2 graph. Okay, so far, just so you guys know, if I go from 0 to 3 pi over 2, it only gives me that much of the graph right there, okay? So then if I go from the window to 2 pi, and then I graph it, it gives me the last piece right here, okay? So we're gonna start here, and we're gonna walk counterclockwise and end up back at 2 pi. So we're gonna integrate from 0 to 2 pi, okay? And we're gonna use our formula, which says, right up here, r squared plus dr d theta squared, okay? So we're gonna integrate r squared, so this would be this 1 r squared would be 1 plus sine theta squared plus dr d theta. So dr d theta equals what? The derivative of sine theta is cosine theta, right? So this would be cosine squared theta d theta, okay? Sorry, I kind of messed that up. So 0 to 2 pi. Now this would be, let's see here, 1 plus 2 sine theta plus sine squared theta plus cosine squared theta d theta. Looks good. I'm just going to see how far we can take this with cleanup. So we know that sine squared plus cosine squared is worth 1. So this is actually 1 right here. And then that's already 1 right there. So that's actually 2. So I'm going to say 2 plus 2 sine theta d theta. And then we're going to have the integral from 0 to 2 pi of the square root of 2 times 1 plus sine theta d theta. And then this is where we would hit somewhat of a roadblock. So this is why they said just set up the integral needed. And I would say that's as far as we're going to go for this class. Okay, you could plug this into your calculator now if you wanted and try to approximate the integral using your calculator and its integration feature, depending on what calculator you have. But that's as far as we'll go with this one. So here's another one that finds the arc length. So this is our L, our arc length. So we can use derivatives of polar coordinates just like we did in Calculus 1, okay? All right, you guys, that's gonna be it for 10.4. We have our exam coming up pretty soon. We are done with chapter 9 and 10. Chapter 9 was all about separable differential equations and linear differential equations. Chapter 10 was all about parametric curves and polar curves and calculus with both of them. Remember, we had to find concavity of parametric curves. Remember, we had to learn how to draw parametric curves with polar curves. We basically, 10.4 is the big deal for polar, taking derivatives of polar curves, taking arc lengths of polar curves, finding the area of polar curves, and finding area inside or outside pieces of polar curves. So that's pretty much what your exam will be on. Please make sure you focus on that, and feel free to ask me questions. All right, you guys, that'll be it for chapter 10.